We have already seen that for any general Markov chain, there is a decomposition of the state space, first into recurrent and transient states, and then the recurrent states can further be decomposed in a finer way into closed irreducible classes. But that we obtain theoretically by showing that the relation of leading to is an equivalence relation on the set of recurrent states. But then the question is, how do we actually identify the decomposition? Certainly not by computing the rho xy's, which is impossible, if not difficult at times. So in these lectures, what we're going to see is essentially a cute way of identifying the decomposition without doing any computation, simply by examining the structure of the transition matrix and then looking at the structure, identifying the minimal subsets of S such that the transition matrix restricted to that subset becomes itself a transition matrix. This will lead to a concept of irreducibility, and then we would examine certain finite state space Markov chains and identify the decomposition. But then some of these things may not work very well for infinite state space Markov chains. So for infinite state space Markov chain, there is no definite algorithm, and therefore we'll see that each has to be examined separately. And in these lectures, we'll see at least two different infinite state space Markov chains and be able to identify their recurrence and transience properties. Okay, we have seen this decomposition of the state space for any Markov chain, namely, firstly, S is union of transient states, ST, and then the recurrent states are decomposed into closed irreducible classes, C1, C2, etc. We've also seen that if we can identify this decomposition, then it will help us to get a clearer picture of the evolution of the chain that was seen. Now, the question is, how do we get this decomposition? Recall that this decomposition is completely based on the quantities rho xy, because that gives us the binary relation of leading to, and from that we get the decomposition C1, C2, etc., etc. But then these rho xy's are in turn completely determined by the transition probabilities pxy of the Markov chain. So at least in principle, if one knows the transition probabilities, then one knows the rho xy's. So as I said, in principle, given the transition matrix for a chain, we should be able to get the decomposition. But in practice, it's not at all easy. In fact, may often be almost impossible. Just to clarify the point, how do we actually go about computing the various rho xy's from the transition probabilities? Let's ask this question. Well, the simplest idea that may come to mind is to observe that, first of all, rho xy is 1 minus px of ty is infinite, which is 1 minus limit n that px probability ty is greater than n. So these are the quantities that we have to compute in order to compute rho xy. So we could try to compute px of ty greater than n for every n using the transition probabilities. Now what is the formula? But the formula for px probability that ty greater than n in terms of the transition probabilities is, remember, ty greater than n means that y has not been visited up to and including time n, conditioned on the chain starting at x. So of course it's not difficult to write down the probability in terms of the transition probabilities. It will be simply sum pxx1, px1x2, etc., pxn minus 1xn, where the sum is over all possible choices of x1, x2, xn different from y, because y is not supposed to be visited. Now, this is clearly quite complicated, and it's highly unlikely that I would be able to compute these quantities for every n, except possibly in some very simple situations. So the question is, how do we go about it? In principle, it is true that we can write down these things in terms of the transition probabilities, but it's writing down, that's one thing, and getting the values is a completely different scenario. However, there is a way to get around this. In particular, when the state space is finite, there is a simple way to identify not only the transient and recurrent states, but also the full decomposition without doing any computation whatsoever. And what we would try to do is try to understand this, or be convinced at least, by looking at examples. But before that, let's start with a definition. A subset C of S, that is a set of states, is called a closed irreducible class. We have already come across this concept, but we want to see it in a different way. If, firstly, pxy is 0 for every x in C and y not in C, and no proper subset of C has this above property. Of course, one can easily see that the first condition immediately means that if you take any x in C and then add the pxy's over all y in C only, then those sums are all equal to 1. Because in any case, for y not in C, the contributions would be 0. So that means the first condition simply means that the C cross C submatrix of P, namely pxy when xy is restricted to C, is a transition matrix in itself because the row sums are 1, all entries are non-negative. And the second condition says that the no proper submatrix of this has this property. It's a routine exercise. What you can verify is that the first condition, from the first condition you can actually say or conclude that not only pxy is 0 for x in C and y outside C, but even pxy n for every n is 0 for x in C and y outside of C. In particular, if x is in C and x leads to y, then y has to be in C. Because for y outside of C, no pxyn can be positive. And the second condition means that no proper subset of C has this property. In particular, x must lead to y for all xy in C. So therefore, there are looking at closed reducible class, which is actually a consequence of the definition, is that no subset C is closed reducible means that no state in C leads to any state outside of C, and every state in C leads to every state in C. Now, if C in S is any closed irreducible class in S, then we can restrict the original process to a reduced state space C. That means look at the transition matrix by looking at only xy coming from C. That's a transition matrix. And this becomes a Markov chain because if you start in any x in C, you're always going to remain in C. So it's a Markov chain in its own right with state space C and transition matrix given by, we may call it P sub C, which is P restricted to C. This MC on the reduced state space C will have the special property that x leads to y for every x y in C. So here is the definition. A Markov chain with the property that x leads to y for every pair xy of its states is called an irreducible Markov chain. So if C is a closed irreducible class, then the Markov chain restricted to C becomes an irreducible Markov chain. So that's exactly what this says. Now here is an easy, useful fact, which is an easy consequence of what you've seen, and that is, if you have an irreducible Markov chain, either all states are recurrent or all states are transient. That of course comes from the fact that recurrent states can only lead to recurrent states. And in that case, the chain itself is called a recurrent Markov chain or a transient Markov chain. And secondly, if you have an irreducible Markov chain with a finite state space, then all states must be recurrent. That of course again because since it's a finite state space, there has to be at least one state which is recurrent. But then part A, either all states are recurrent or all states are transient, which means in this particular case, all states in an irreducible Markov chain must be recurrent if it has finite states. That is, any irreducible finite state space Markov chain is automatically a recurrent chain. So these are very, very important and useful facts. So now let's get to see how we can put these things to use. Suppose by examining the given original S cross S transition matrix P, by just examining it, but emphasize without doing any computations, suppose we can identify such subsets C in S, which are closed irreducible classes. We'll see how. That is, the submatrix restricted to C, each such C is itself a transition matrix, and these are the smallest such in the sense that none of the C's can be reduced any further to yield submatrix, which is transition matrix. So these are sort of smallest subsets of S where restriction of P remains a transition matrix. We then know that the original chain, when restricted to any such C, is an irreducible Markov chain, and therefore for each such C, either all states in C are recurrent or all are transient. And this we obtain by without doing any computations whatsoever, just by examining the transition matrix, and from the examination, if you are able to identify such C's, so then at least we could say that within each C, all states are transient or recurrent. But even this uncertainty disappears in case we have a finite C, because in that case, we can immediately conclude that all states in C, in a finite C, must be recurrent, as already pointed out. So remember, we are being able to make this conclusion without doing any single computation. This becomes particularly useful when the original chain has a finite state space, because in that case, all C, closed irreducible C, will also be finite. Okay, as I said, now to see how all these work wonderfully for a finite state space Markov chain, let's start with an example. First example is, consider a Markov chain with state space 6 states labeled as 1, 2, 3 up to 6, and suppose the transition matrix is this 6 cross 6 matrix. Now, what we said is, given this transition matrix, we are required to examine this matrix without doing any hard computations and see if we can identify some subset C of S which are closed irreducible, that is, which are themselves transition matrices, that is, submatrices restricted to those sets are transition matrices, and this is the smallest one. Now, a quick scrutiny of the matrix P, but no computations, tells us that if we look at C1 consisting of the states 1 and 2, that is, look at the left uppermost corner of two states, 2 by 2 matrix, it is immediate that that is a transition matrix, and no smaller subset would be a transition matrix. So that is one possible C. Another C, which is we call C2, is if you combine 4 and 6. So if we look at the states 4 and 6, that is the rows and columns corresponding to only 4 and 6, again you can see you get a submatrix whose entries would be half-half, 2/5, 3/5. That's a transition matrix. I'm looking at only rows and columns corresponding to 4 and 6, and you see that these are closed irreducible, and these are the only ones. By the above proposition, we conclude that 1, 2, 4, 6 are recurrent state. So you see, we didn't do any computation, we didn't compute any rho xy or anything like that. Straight away by this scrutiny of a quick examination of the Markov transition matrix P leads us to this conclusion that 1, 2, 4, 6 are recurrent states at least, immediately. Well, what about the states 3 and 5? We haven't said anything yet. Claim they are both transient. Again, without any computations. Why? Well, you can immediately see that 3 leads to 1. In fact, if you go back to the matrix, P31 is 1/4, which is positive. So it's possible to go from 3 to 1 in just one step with positive probability. So 3 leads to 1. But 1 is in C1. Therefore, 1 doesn't lead to any state outside of C1. In particular, 1 does not lead to 3. Now, this would be impossible if 3 were recurrent. And the argument is similar for the other state 5. So you see, without doing any computation, without dirtying our hand with any algebra, for this particular Markov chain, we have been able to identify that 1, 2, 4, 6 are recurrent, 3 and 5 are transient, 1, 2 forms one closed irreducible class, and 4, 6 forms another closed irreducible class. So what we saw in this above example is in fact true for any finite state space Markov chain, and here's the general algorithm. Given the S cross S transition matrix P of the chain, try to identify all the minimal subsets C of S such that C cross C submatrix of P corresponding to states in C is a transition matrix, but no proper subset is. Now, for a finite state space Markov chain, there will always be at least one such C. Try to understand why. Then each such C is a finite closed irreducible class. Therefore, all states belonging to such a C are recurrent. States, if any, not belonging to any such C have to be all transient. So that's the general algorithm, and we can make these conclusions without doing any computations. Only thing it rests on is you're being able to identify, just by looking at the transition matrix P, identify these minimal subsets C. Let us see one more example. Here there are 4 states, and the transition matrix are given by this. Now here you can do this as exercise, verify that in this particular case, for every xy in S, x leads to y. For example, 1 leads to 1, 1 leads to 2, 1 leads to 4. In one step itself is clear. Does 1 lead to 3? Well, 1 leads to 2 in one step, and then 2 leads to 3 in one step. So therefore 1 leads to 3. 1 can go to 3 in 2 steps with a positive probability, and so on and so forth. You can argue that, in fact, you can see that 1 leads to 2 leads to 3, and 3 leads to 4, and 4 leads to 1, and all these are in one steps. So what this means, and now using the fact that this leads to is a transitive relation, you can then conclude that every x leads to y for every xy in S. So what that means is that there is no proper subset of S which is closed and irreducible, because every state leads to every state. So in other words, the given Markov chain here itself is irreducible, and since the state space is finite, all the 4 states are recurrent. Once again, we have made this conclusion without doing any computations. Now, what we saw in this above example can happen at times. Now, when this happens, that is, if x leads to y for all xy in S, the given chain itself is irreducible. And since the state space is finite, all states are automatically recurrent. Thus, such a chain, irrespective of how it starts, will visit every state in S an infinite number of times with probability 1. Another example of such a finite state space irreducible chain is this example 3. Recall the definition of Ehrenfest diffusion chain, where d balls are distributed between two chambers of an urn, and at each turn one ball is selected at random and transferred from that chamber in which it was to the other chamber. Let xn denote the number of balls in chamber 1 at time n. Here the state space is 0, 1, 2 up to d, and the transition probabilities, as we have already seen before, are given by px x minus 1 is x over d, and that is same as 1 minus px x plus 1. That means x to x plus 1 transition probability is x by d, and x to x plus 1 transition probability is 1 minus x over d. Now again, one can easily verify that this is also an irreducible chain, and the reason is not so difficult to see. From any state, let's say from 0, you can go to 1 in one step with probability, positive probability. From 1 you can go to 2 with positive probability. So therefore 0 leads to 1, 1 leads to 2, therefore 0 leads to 2. In general, from any state you can go to any state y larger than that. Similarly, suppose you start from, let's say, d. From d you can go to d minus 1 in one step. So d leads to d minus 1. From d minus 1 you can go to d minus 2 in one step. So d minus 1 leads to d minus 2. So d would lead to d minus 2. And this way you can show that every state x leads to every state y which is strictly less than. So x leads to y for every y greater than x, and x leads to y every y less than s. Now showing that x leads to x is just x leads to x plus 1 and x plus 1 leads to x. So one can easily verify that this is also an irreducible chain, and therefore all states are recurrent. Now in all the examples so far, we have only considered Markov chains with finite state space. The finiteness of the state space was crucial in making definite conclusions that we could because of the following reasons. When the state space is finite, there has to be at least one recurrent state. As a consequence of the above, all states in a finite state space irreducible Markov chain are recurrent. Now this is something, both these factors are because of the finiteness of the state space. Unfortunately, none of the above would hold for chains with infinite state space. Therefore, unlike finite state space Markov chain, where we had a definite algorithm that was described a little while back, leading to an easy identification of recurrent and transient states, such general algorithm would not be there in the infinite state space situation. So each chain has to be analyzed separately, and we will examine later some specific examples to get an idea of how to go about it. So we will look at some infinite state space examples to see how to decide on recurrence and transience of states. Here, as already pointed out, there is no general algorithm, so each particular example would have its own technique. So it's important to understand these examples and particularly the techniques used in each example. So we start with simple random walk because that's one of the simplest ones to examine. So recall that it's a Markov chain whose state space is all integers, and the transition probabilities are given by px x plus 1 is theta and px x minus 1 is 1 minus theta. Here we assume that theta, which is a quantity strictly between 0 and 1, represents the win probability or the probability of heads at each stage. Of course, observe that x leads to x plus 1 and x leads to x minus 1 from the definition. Now, using transitivity, you can conclude that x leads to y for every xy in S. For example, x leads to x plus 1, x plus 1 leads to x plus 2, so x leads to x plus 2. And similarly, x leads to x minus 1, x minus 1 leads to x minus 2, so x will lead to x minus 2. So using this recursively, you can show that x leads to y for every y greater than x and every y less than x, and then you can say that x leads to x plus 1, and then in turn x plus 1 leads to x, so x leads to x. So we conclude that the chain is irreducible. However, unlike in the case of finite state space, we cannot immediately conclude that all states are recurrent. This is what we would have done had it been a finite state space situation. So what can we do? Well, let's first observe one thing. Since the chain is irreducible, only one of the two possibilities exists. Either all states are recurrent or all states are transient. It therefore suffices to focus attention on any one single state and try and see if that state is recurrent or transient. Depending on our conclusion on that one state, we will be able to say what is true of all the states. In fact, we will take the state 0 and examine whether 0 is recurrent or transient. And the criterion for deciding whether 0 is transient or recurrent, we would consider that criteria where we have to look at the infinite series P00 super n and examine its divergence or convergence. Now, this may seem very difficult at the first sight, but we'll actually be able to do it without having to engage in much tedious computations. First, observe that this chain, having started at 0, cannot return to 0 in an odd number of steps. Because remember, every step is either going one step up or one step down. So starting from 0 to come back to 0, you have to have as many upward movements as downwards. So it's possible to come from 0 to 0 only in an even number of steps, which means P00n is 0 for every odd n. Therefore, the above series reduces to sum over n, but P00 2n. Now, from the dynamics of the chain, one can easily see that this probability P00 2n is nothing but 2n choose n times theta into 1 minus theta to the power n, true for all n greater than or equal to 1. It is simply saying that in order to return from 0 to 0 in 2n steps, among the 2n steps, exactly n have to be upward, n have to be downwards. N wins, n losses. And of course, that can happen. The probability of that is precisely this. It's a binomial probability that in 2n tosses of a coin, what's the probability of having exactly n heads and n tails? Heads probability is theta, 1 minus theta is the tail probability. So now we have to decide on the divergence and convergence of this series. Of course, this looks pretty difficult as it stands, but we use this fact from calculus, very important fact from calculus. So what is that fact? First of all, given any two non-negative sequences an and bn, that is sequences of non-negative real numbers, we say that an is equivalent to bn if an over bn goes to 1. Since we are writing an over bn, that means we are assuming that they are positive real numbers. So here's the fact. Given non-negative sequences an and bn, with an and bn of the same order, the series an converges or diverges according as the series bn converges or diverges. That is, if you have two sequences here of the same order, then either both of them converge or both of them diverge. In other words, if you know the convergence or divergence of one series, then from that itself you can conclude convergence or divergence of another series. So what we'll do in our case is, we will find a non-negative sequence bn such that 2n choose n times theta 1 minus theta to the power n is equivalent to bn, and then use convergence or divergence of the bn series to conclude the transience and recurrence, transience or recurrence of 0. And to get to that, what we use is a very well-known result in probability and mathematics called Stirling's formula. So what does it say? It says that n factorial is of this order, some constant alpha positive times e to the minus n times n to the power n plus half. Using this, one can deduce that for some constant beta, positive constant beta, the constant doesn't matter much. This quantity P002n, which is 2n choose n theta into 1 minus theta to the power n, is equivalent to beta times, that constant beta times, 1 over root n times 4 theta 1 minus theta to the power n. So the question now is about finding convergence or divergence of this series. Because whatever we can say about convergence, divergence of the series, this series, the same would follow for the series that is in question. Of course, this clearly depends on the value of the quantity 4 theta into 1 minus theta. Now, using basic calculus or even the AMGM inequality, one can see that 4 theta into 1 minus theta is less than or equal to 1 always for all theta between 0 and 1. And this inequality is strict inequality if theta is not half. Of course, if theta is half, then it's equality. Which would mean that this series converges if theta is not half. Why? Because in that case, 4 theta into 1 minus theta is strict less than 1. So you have a geometric term divided by root n, and even if you ignore the root n, 1 over root n, because that is anyway less than or equal to 1, you have a geometric series with 4 theta 1 minus theta strict less than 1, and that series converges. So if theta is not half, it converges. If theta is half, then 4 theta 1 minus theta is 1, so that to the power n is 1. So you end up getting the series 1 over root n, which of course we know diverges. So therefore this series converges if theta is not half and diverges if theta is half. So we conclude that 0 is recurrent or transient according as theta equals half or theta not equal to half. Using irreducibility, from this we now conclude that the simple random walk is recurrent or transient according as theta is half or theta is not equal to half. Now the transience of simple random walk for the case theta not equal to half is not so unexpected. You can also sort of argue it as a consequence of something that you probably know from undergraduate probability, which is called strong law of large numbers, a very important result in probability and statistics. What does it say? It says that if you have IID random variables xi1, xi2, xi3, etc. with finite common mean mu, then the average xi1 plus xi2 plus xin by n converges to mu with probability 1. Now recall that the simple random walk is defined as xn equals x0 plus the sum of the xin, xi1 plus etc. up to xin, where x0 is the initial state and xi1, xi2 are IID random variables, each taking values plus or minus 1 with probabilities theta and 1 minus theta. Now given that x not equal to 0, strong law of large numbers would imply that xn over n would converge to mu with probability 1, where mu is the common mean of the xi's. Now the common mean of the xi's, which take the value plus or minus 1 with probabilities theta and 1 minus theta, is 2 theta minus 1. So when theta is not half, we have mu is not equal to 0, which would mean that xn over n converges with probability 1 to something of constant which is non-zero constant, and now depending on whether it's a positive constant or a negative constant, you can conclude that xn would go to plus infinity or minus infinity with probability 1. That depends of course on whether mu is positive or negative. What this says is that the chain starting from 0 will with probability 1 eventually get out of any finite bounds for good. So there is no way that the chain starting from 0 will return to 0 infinitely often. Remember, that is required to happen, in fact, with probability 1 if 0 had to be recurrent. So therefore 0 and hence all other states, because of irreducibility, must be transient. So this is a consequence of law of large numbers in case theta is not half. What is not so easy to understand is the recurrence of the simple random walk when theta is half. In this case, mu is 0. So an application of strong law of large numbers, we now say that given that the walk starts at 0, xn over n goes to 0 with probability 1. But for xn by n to go to 0, it is not at all necessary that xn has to become equal to or even come close to 0 for infinitely many n. Thus, infinitely many returns to 0 happening with probability 1 is by no means an obvious fallout of law of large numbers in this particular case. Anyway, in fact, even for general random walk on integers, the above phenomenon is common, namely, the random walk is recurrent or transient according as the common mean of the underlying xi sequence equals 0 or not. We don't prove this. Once again, transience in case of non-zero mean is easy to understand from strong law of large numbers, but recurrence in case of zero mean does not have an easy explanation based on law of large numbers. Our next example, again of an infinite state space Markov chain, is a renewal chain. Recall that the renewal chain, every time an item is in operation breaks down, it is replaced by a fresh item at the start of the next day. So xn indexed by n greater than or equal to 0 is a Markov chain where state space is natural numbers and xn denotes the age of the item in operation on day n. Denoting the life of a typical item by random variable generic notation L with values in n, the transition probabilities of the chain are given by, so this is something that we've already seen before when we first introduced this as an example. These are the transition probabilities. So everything is expressed in terms of the common lifetime distribution, that is the distribution of capital L. Note that by declaring the state space of the chain to be all of natural numbers, we have tacitly, without making it explicit, assumed that the lifetime is not a bounded random variable. That is, we are not assuming that 80 is the maximum life or 100 is the maximum life. We are not assuming anything like that. Which means that we are assuming that for every x in n, probability that L greater than or equal to X is positive. And that is something that is crucial in the definitions of the transition probabilities, where in all cases probability L greater than or equal to X appears in the denominator. Okay, because why unbounded? Because had that not been the case, that is, had L being a bounded random variable with M being the maximum possible value of L, then clearly the state space would have been simply 1 to up to M, because no item would have lasted for more than M days. So we continue with this assumption of L not being bounded. That is this. This will in particular ensure that Pxy as given above are all well defined, and further Px x plus 1 is strictly positive for all x. That comes from the formula for the transition probabilities. And also Px1 is strictly positive for arbitrarily large x. So from this you should be able to deduce that x leads to x plus 1 for all x and x leads to 1 for arbitrarily large x. This in conjunction with transitivity can be easily seen to imply that the chain is irreducible, but do this as an exercise. So as in the case of simple random walk, it's enough to focus on any one state. In this case, we'll focus on state 1 and determine whether that is recurrent or transient. To this end, we'll actually try to compute P1 probability that T1 is greater than n, and then take the limit as n goes to infinity. So remember, this is a completely different approach. So here we are, rather than going to the testing the convergence or divergence of a certain series, we are directly looking at focusing on rho 1 1, trying to find rho 1 1 and seeing whether rho 1 1 is 1 or less than 1. So from the dynamics of the chain, it's clear that P1 probability that T1 is greater than n means starting from 1, coming back to 1, that time is more than n. That means if given that the item in operation on day 1 has age 1, you haven't, the time to return to that same state has not happened until time n. That means the same item which has been in operation on day 1 has continued happening. So that means that x2 is 2, x3 is 3, etc., xn is n, given x0 equal to 1, and that simply means it's a probability that L is greater than or equal to n. Just try to convince yourself that that is the case. It's not difficult. Now from this it follows, therefore, that P1 probability that T1 is infinite would be the limit of this, which is limit of P1 probability that L1 is greater than or equal to n, and that of course 0 is because tail probabilities go to 0. So that immediately tells you that rho 1 1, which is P1 probability that T1 is finite, is 1, implying that 1 is recurrent. And therefore by the irreducibility of the chain, we conclude that all states are recurrent. Of course, the analysis in case L is bounded, say when the maximum possible value of L is M, is even easier, because then the state space is finite. So from irreducibility, one can directly conclude recurrence of the chain. Okay, what we have just now seen is for finite state space Markov chain, there is a definite algorithm to get the decomposition, and you end up getting a bunch of closed irreducible recurrent classes, and maybe there are some transient states, if any. But then we saw two very important infinite state space Markov chains also. One is simple random walk, where we saw that recurrence or transience depends on the value of the probability of heads or tail, whereas for renewal chain, which is the other infinite state space Markov chain that we studied, we saw that it is always recurrent. That means it's irreducible and all states are recurrent.